Hello, this is Math Jazz from Almost Cool. Today we are going to be going over some concepts that are highly involved in calculus. This is going to be a diagnostic test on pre-calculus subjects or subject matter. So without any further ado, let us pull up our first problem. We're going to talk about evaluating exponential expressions right now. So I have some problems on the board, and we're going to start working on them. So the first one was -3. My board isn't working right now. Let me check the cables. Okay. There we go. Okay, so we have -3 raised to the 4th power. So I guess first thing that we want to go over is we want to talk about what are the rules that we have for exponents. So this expression, a raised to the b, is equivalent to a times a times a b times. So this here, -3 to the 4th, is equal to -3 times -3 times -3 times -3. There are 4 -3's being multiplied together. And so, to simplify this, we can do it a number of ways, but let's just start from one side and multiply until we get to the other. So -3 times -3, the two negative signs cancel out, so we'll get a positive number. 3 times 3 is 9, so now we get 9 times -3 times -3. Well, I guess the other thing is that since we have -3 times -3 is 9, the other -3's multiplied together will also be +9. So this is going to be another 9 here. So we get 9 times 9, which is 81. And so this here is the answer to our first problem, 81. Let's look at our next problem. We have -3 to the 4th. Okay, so this is illustrating some aspects of the notation that we need to make sure that we get right. So this first problem that we had here, the -3 was inside parentheses, and those parentheses were raised to the 4th power, or everything inside the parentheses were raised to the 4th power. So in this new problem, we have a -3 to the 4th, and the way that we deal with this, the exponent only affects this base here, this 3, and this negative sign is considered to be out in front of it. So I guess this -3 to the 4th is the same as saying -3 raised to the 4th, like that. These are the same thing. And the reason that we do this is we had to make a choice as mathematicians. How are we going to represent the concept of 3 times itself 4 times a negative sign, and -3 times itself 4 times? So we have to have ways of writing down both different ideas, and the way that we chose to do this is the how we decided to have parentheses and exponents mix with each other, play with each other. So this top one, the negative sign is considered inside the exponent, and we have to multiply that negative sign by itself several times. The second way for the second problem is not like that. The negative sign is applied after the fact. So this is going to be -3 times 3 times 3 times 3, which is the same as -3 9 times 9, because these two 3's multiply to 9, those two 3's multiply to 9, so we have 9 times 9, which is 81, and the negative sign came along with us through the whole ride until the end there. So we have negative 81 as the answer. So notice that the first one came out as positive 81, the second one came out as negative 81. So it's important to keep track of those negative signs and make sure that they go that you perform all of the operations appropriately on them. Okay, so let's look at our next problem. Our next problem is 3 to the negative 4th. So let's scroll down a bit. So I defined our exponent as repeated multiplication. So we had 3 to the 4th was equal to 3 times itself 4 times. Well, what would a negative exponent mean then? Okay, so the way that we define our negative exponents is, so let's say we have, let's first look at a different problem, and we'll come back to this one, where we're going to use some positive exponents. So we have, say, 3 times, or 3 squared times, let's say, 3 to the 3rd. So this here, the problem, we have 3 times itself 2 times, so that's 3 times 3 times, and we have 3 to the 3rd, which is 3 times 3 times 3. Notice that that's 1, 2, 3, 4, 5 3's together, so that's 3 to the 5th. And notice when we look at our exponents, we have this 2 plus 3 equals 5. Now, if the bases of our exponents are the same, so if we have base times a base, and we have an exponent and an exponent, let's use a different letter. So we have b to the a, base to the a, times base to the c. Since the bases are the same, it'll always be the case that b to the a times b to the c is equal to b to the a plus c, like so. And I'm not going to prove this rule. I think that there's a proof of this in my exponential video on the channel, so you can go take a look at that if you'd like a proof. For now, we'll just claim that this is a true statement. And now, what we have to do now is go back to our idea of what do we have when we have 0 and negative integer exponents. What would that mean? So we had 3 to the negative 4. Well, what we want 3 to the negative 4 to equal is we want it to equal something such that if I go 3 to the 4 times 3 to the negative 4, I get 3 to the 4 minus 4, which is 3 to the 0. 3 to the 0, anything to the 0 power is equal to 1. So any base raised to the 0 power is equal to 1. And the reasoning that we give for this is in my exponential video. But the idea is that if I have, let's say, 3 to the 2, that's 3 times 3, that's 2 3's. 3 to the 1 is going to be 3. 3 to the 0. Well, to get from 3 squared to 3 to the 1, I divided by 3. To get from 3 to the 1 to 3 to the 0, I will also divide by 3. So let's put 3 to the 3rd here above everything. So we get 3 to the 3rd equals 3 times 3 times 3. Oops. And every time we reduce the power by 1, going from 3 to 2, we cancel to 3. 2 to 1, we cancel to 3. Going from 3 to the 1 to 3 to the 0, we'll cancel a 3. We'll divide by 3, and that leaves us with 1. 3 divided by 3 is 1. So that's kind of our heuristic reasoning for anything to the 0 being 1. And if you'd like more depth on that, there's a video on the channel. Anyway, so if 3 to the 0 is 1, then 3 to the negative 4, we want 3 to the 4 times 3 to the negative 4 to equal 3 to the 0, which is 1. Well, 3 to the 4 is 3 times 3 times 3 times 3. This is 3 to the 4. And we want that times 3 to the negative 4 to equal 1. So that means that 3 to the negative 4, well, if we divide both sides by 3 times 3 times 3 times 3, we get that 3 to the negative 4 is equal to 1 over 3 times 3 times 3 times 3, or it's equal to 1 over 3 to the 4. So a negative exponent just takes whatever you're looking at and flips it into the denominator of your fraction. And of course, every number is a fraction. And if it doesn't look like a fraction, that's because the denominator of that fraction is 1. Okay, so I guess getting all the way back to the original statement of the problem, we wanted 3 to the negative 4, and we wanted that in an expression with no exponents. So that's going to be 1 over 3 to the 4, which is going to equal 1 over 3 times 3 times 3 times 3, which, as we recall, is 81. So 3 to the negative 4 is 81. And returning to the problem list, we have 5 to the 23 over 5 to the 71. Let me take a closer look at that. That looks pretty huge. Yep. 5 to the 23 over 5 to the 21. Oh, I thought it said 71. It says 21. That's better. Okay, so we have 5 to the 23 on top over 5 to the 21. That's going to be the same as 5 to the 23 times 5 to the negative 21. Because if negative in our exponent just flips our fraction over, then we'll just flip this fraction over like that. But multiplying things with the same base is just adding the exponent. So that's 5 to the... This should be 23 here. Why, this eraser is so small. Okay. So we have a 5 to the 23 times 5 to the negative 21, which is 5 to the 23 plus negative 21, which is equal to 5 to the 2. 23 minus 21 is 2. 5 times 5 is 25. And there we have it. So 5 to the 23 over 5 to the 21 is 25. And we will look at our next problem. We have 2/3 to the negative 2. So this negative sign will allow us to flip our fraction over. So we get 3 over 2 to the 2. When we distribute, we get 3 squared over 2 squared, which is a rule that I haven't shown you, that you can distribute exponents over fractions, but I think it's in the exponential video on the channel. So 3 to the 2 is 9, 2 to the 2 is 4. The answer is 9/4. Okay, so we'll give ourselves a little bit more space now. Go. And we will move on to our next problem. So our next problem is 16 to the negative 3/4 power. There you go. 16 to the negative 3/4 power is equal to 1 over 16 to the 3/4 power, which is equal to we're going to split this into 1 over 16 to the 1/4, all raised to the 3/4, to the third. So this is a rule that we haven't gone over in this video. It's in our exponential video. But the numerator, when we have a fractional exponent, can be pulled out as its own exponent. We're going to split this one exponent of 3/4 into two exponents. One of them being 3, and the other one being 1/4. So, now that we have this split up like this, we want to know what is the fourth root of 16. Or in other words, what times itself 4 times is 16. And you might not have this memorized, but if you don't, we'll just take 16 and start factoring it. So first thing to check is this even? Yes, it is. So there's a 2 that factors out of it. What times 2 equals 16? 8. Okay, so we factored out a 2. 2 is a prime number, so we're done with that. 8 is not a prime number, so we check, is it even? Yes, it is. So 8 will factor into 2 and 4. 2 is prime, so we're done with that branch. 4 is not prime, so we'll factor that again. Is 4 even? Yes. 2. 2 times what equals 4? 2. And now we're done. We have all prime factors, and we say, okay, well, if we have a 1/4 power, we can cancel our factors in groups of 4. Turns out we have exactly 4 2s, so this 16 to the 1/4 is equal to 2. It was in the fraction, and that fraction was being raised to the third, so we leave the rest of that alone. We only handled 16 to the 4th there. So 16 to the 4th was 2. We left it at the bottom of this fraction, and we left the fraction being raised to the third, and we'll move to the next step. So 1/2 to the third is the same as 1 to the third over 2 to the third. 1 to the third is 1. 1 to any power is 1. And then 2 to the third is 2 times itself. 3 times 2 times 2 is 4. Times 2 again is 8. So we get 1/8 as our answer. Okay, so that wasn't so bad. And I think, are we done with, yes, we're done with that section of exercises. So let us move to our next problem. Our next problem says simplify each expression, write your answer without negative exponents. And we'll zoom in a little bit. So we have to figure out how to rewrite these without any negative exponents. Okay, so simplify is kind of a strange term in mathematics. Simplify almost always depends on what it is that you're trying to do. So, we're going to assume that in statement A that we're wanting to combine these radicals, okay? Now, there may or may not be a good reason, well, there are good reasons for removing radicals from expressions, or by combining radicals. But as I said, simplify depends on what you're trying to do. So I think that that's a pretty good guess, though, as to what they mean by simplify here. So we're going to try and turn the square root of 200 minus 32, or the square root of 32. We're going to try and combine these into one radical symbol. Now, there are a few techniques by which we could do this. I'm going to show you one technique first that I think is the easiest one, but it also requires you to recognize factors inside of this expression. So it's probably the easiest to do, but it's probably the harder one to see. It takes a little bit of inspiration to do it, maybe. So I'm going to notice that that 2 and 5 go into this radical here, and 2 goes into this radical here. So we're going to go like this. 200, if we factor it, it's going to be 4, let's do this nice and slow. So this is 2 times 100, which is 2 times 2 times 50, which is 2 times 2 times 2 times 25, which is 2 times 2 times 2 times 5 times 5. And the square root kills factors in pairs. So we can kill off 2 of the 2's and 2 of the 5's as follows. So these 2 2's become a single 2 outside. These 2 5's become a single 5 outside, and we're left with a 2 all by itself left inside the radical. That's 2 times 5 times the square root of 2. Minus, now 32 also has some factors to it. So let's factor 32. 32 is equal to 2 times 16, which is 2 times 2 times 8, which is 2 times 2 times 2 times 4, which is 2 times 2 times 2 times 2 times 2. And again, we can cancel out pairs of common factors. So these 2's and those 2's come out. So this is 1 2 that comes out, and this is another 2 that comes out. Now we get left with 4, or 2 times 2 times the square root of 2. So we get 10 radical 2 minus 4 radical 2 equals 6 radical 2. I think this is the easier way to do it, because you can just look at this, and if you're pretty good at factoring, you could look at this and say, oh, this is 10 root 2. You might do it like this. 200 equals 2 times 100. 100 is a perfect square. So we just take it out as 10 root 2. You might have done that. 32, you're like, okay, so this is 2 times 16. 16 is a perfect square, so you take that out as its square root. 4 times root 2. 10 minus 4 is 6. So it's pretty, I think, pretty easy to get there this way. However, if you don't see the common factors between these radicals, you might need to use a more complicated technique called rationalizing the numerator. And we're going to do that right now. So we had square root of 200 minus square root of 32. And if you're wondering, why are we doing this in a more complicated way? Well, you're going to need to learn how to rationalize the numerator, rationalize the denominator of a fraction, because there are times when it's really useful and there are no other methods that will solve the problem. So, whereas this problem was able to be solved through some factoring, it's nice to practice this more difficult technique on this problem, because this is a problem that we feel comfortable with now. We have a solution to it. And we're going to practice a more difficult technique here of rationalizing, so that when we come up to a more complicated problem that needs a more complicated method, like rationalizing, we feel comfortable with it. So, and one of the pros of rationalizing the numerator is that it doesn't require any sort of guesswork. Guesswork is probably not the right term, but it requires no inspiration. There's no, oh, I look at that and I see there's a 10. There are 2 10s as factors, and so I can take the square root of 100 there and get 10. I don't have to try and remember or recall or be inspired to things. It's very mechanical. There are no guesses to be made. Okay, so what I'm going to do here is I'm going to turn this into a fraction by putting a 1 in the denominator. And I am going to multiply this fraction by another fraction, which is going to be the same as the top, so 200 and square root 32, but I'm going to flip the sign in the middle. And I'm going to have the same number in the denominator, 200 plus square root 32. And since this fraction is something divided by itself, this fraction's total value is 1. Multiplying by 1 doesn't change the value of something. So I am not changing the value of my original expression, which is square root 200 minus square root 32. So I can do all of this manipulation so far without changing the value of what I'm looking at. And that was the whole goal, is to try and figure out the value of this expression. So this is not changing any values, but it's going to have some interesting properties. When I multiply across, 1 times 200, or square root 200 plus square root 32 is going to be just itself. Square root 200 plus square root 32. There we go. And then the top, I get square root 200 times square root 200 is 200. I get negative square root 32 times square root 200 is negative root 32 minus, times square root 200. That's first times first, second times first. We'll go first times last. We get plus square root 200 times square root 32. And then we'll get minus, well, square root 32 times square root 32 is 32. So we get this. But if you notice, the middle two terms cancel out. And so we get 200 minus 32, which is going to be 168 over square root 200 plus square root 32. So now we have the problem of, oh, this is actually a fairly interesting thing. You cannot get rid of sums or differences of square roots using rationalization. So I just realized that I hadn't thought of it before. This here is equal to our original number, and it's also equal to 6 root 2, which is how we simplified it the first time. This expression here looks more complicated than the original one, because it probably is. But it was good to learn this technique of rationalizing a numerator or a denominator. Notice the thing that happened here is it turned, we used to have, the numerator had square root signs in it, and now it does not. It turns out that rationalizing the numerator or rationalizing a denominator will always have this effect. Wherever the square roots are, they will go away and end up on the other side of the fraction. So there are a couple of times where this is useful. Particularly, we're going to use it when we are proving the power rule for the square root function, when we get to proving derivative rules in chapter 3. Okay, so this is something to look forward to. This technique here of multiplying an expression with radicals by a fraction where we switch the signs. That's called rationalizing the numerator if our radicals were in the numerator to start with. It's called rationalizing the denominator if the radicals are in the bottom. But this technique is something that will come up, and it is on the practice test. In fact, as we keep going today, we're probably going to run into a problem that requires this technique. And we've seen it now, and we'll be ready for it when we need it. Okay, so let us move on to our next problem. We have 3a cubed b cubed times the square of 4ab squared. So copy that. 3a cubed b cubed times the square of 4ab squared. And it looks like this. So, going from here, we want to handle this part of our expression. We distribute this square to each of the terms inside of the expression. So we get 3a cubed b cubed times 4 squared times a squared times b squared squared. That's going to equal, well, 4 squared is 16, times 3 is 48. Now we have a squared times a cubed is a to the 5th. Now we have b squared. Squared is going to be, when you have an exponent, when you have something raised to a power, all raised to another power, the rule is it's going to be your base raised to the product of the two exponents. So this will be c times b. So 2 times 2 is 4. This is going to be b to the 3rd times b to the 4th. 3 plus 4 is 7, so we get b to the 7th. And this is our answer. 48, a to the 5th, b to the 7th. Okay. And we have one more expression here. And let us read it off. We have the negative second power of the fraction, or of the quotient of 3x to the 3 halves, y to the 3rd, and x squared, y to the negative 1/2. There we go. We have this fraction right here. And we're going to take it and rearrange it. So the first thing to do is we're going to handle this negative sign. That'll flip our fraction over. So we'll get x squared, y to the negative 1/2 over 3x to the 3 halves, y to the 3rd, everything squared. Next, we'll handle the second power. So we get, I'm going to keep going sideways. We get x to the 2 to the 2. So we just multiply this 2 and this 2. We get x to the 4th. This is y to the negative 1/2 to the 2. So that's going to be negative 1/2 times 2 is negative 1. On the bottom, we have 3 to the 2 is 9. We have x to the 3 halves to the 2. So 3 halves times 2 is 3. So that's x to the 3rd. So we have y to the 3rd to the 2. So 3 times 2 is 6. We get y to the 6th. We keep going. We have this y to the negative 1 here. It's going to come down into the denominator. And that'll give us, well, the negative sign flips this y into the denominator. So we have y to the 6 times y to the 1. 6 plus 1 is 7. So we're going to get y to the 7th. That handles this part of the expression. The 9 is left alone. Then we have x to the 4th divided by x to the 3rd. So that's, if we pull this x to the 3rd up, that means we get x to the negative 3rd. X to the negative 3rd times x to the 4th is the same as x to the 4 minus 3. 4 minus 3 is 1. So we're going to get an x in the top. But we're going to clean up this fraction here. We get x over 9y to the 7th. This is our fraction. And now we have to go to the next section of the textbook. So, expand and simplify. So, all we're going to do in this one is multiply everything out that needs to be multiplied out. So, we have 3 times x plus 6 plus 4 times 2x minus 5. We distribute, and we get 3 times x is 3x. 3 times 6 is 18. 4 times 2x is 8x. 4 times negative 5 is negative 20. And then we simplify. 3x plus 8x is 11x. 18 minus 20 is negative 2. And that is our simplified expression. Let's go to the next one. Oh, this one here looks a lot like it's rationalizing an expression. It's not exactly that, but it looks a lot like it. This is called multiplying by the conjugate. Our expression a plus square root a plus square root b times the quantity square root a minus square root b. So if this is an expression, this is the conjugate of that expression, because we take this sign here between our two square roots and we flip it. Likewise, if this is our expression, that's the conjugate of it, because we took this sign between these two, this addition or subtraction sign, which is a subtraction sign here, between these two radicals, and we switched it. That gives us the conjugate. So whenever you have an expression that has square roots in it, and you flip the sign between two of them, you get the conjugate. Okay, so we get square root a times square root a is a. Then we get square root a times negative square root b is negative square root a square root b. The next one is square root b square root a. And the last one is minus b. And we notice that these middle terms cancel out. So we're left with a minus b. Okay. And the last one here is x plus 2 to the third, which is going to be x plus 2 times x plus 2 times x plus 2, like so. Now, there are other ways of doing this. If you remember the binomial theorem, which I don't think we cover in this class, there's a way of doing this directly. However, we're just going to multiply this out. So we're going to multiply two of the terms first, let's say those two, and then multiply it by x plus 2 after the fact. So x times x is x squared. 2 times x is 2x. That's these and then these. Now we need to get this and then this. So we have the next one is 2x as well, and the last one is 4. We're multiplying that by x plus 2. But first we're going to combine some x, the two terms here that we can combine. So we get x squared plus 4x plus 4 times x plus 2. So we get x times all of this is going to be x cubed plus 4x squared plus 4x. 2 times this is going to equal 2x squared plus 8x plus 8. And adding all of that together, we get x cubed plus 6x squared plus 12x plus 8. That is our expression completely multiplied out. Let's go back to our list of problems, and we will check these problems now. So we have x plus 3 times 4x minus 5. Like so. We're just going to multiply the first times the first, so we get 4x squared. We get 3 times 4x is plus 12x. We get negative 5 times x is minus 5x, and then we get 3 times negative 5 is negative 15, and we combine that to get 4x squared plus 7x minus 15. And our next problem, we get 2x plus 3 squared, which is equal to just 2x plus 3 times itself. So we get 2x times 2x is 4x squared. We get 3 times 2x is 6x. We get 2x times 3 is 6x. And we get 3 times 3 is 9. And we add those together to get 4x squared plus 12x plus 9. Okay. So these aren't ending up being too bad. Okay. Let's look at the next one. Factoring expressions. Okay. So let us practice factoring some things. We have 4x minus 25, or 4x squared minus 25. There we go. So this is called a difference of squares. So notice that 4 is a square, x squared is a square, and 25 is a square. And when you're factoring a difference of squares, you just take the square root of the first thing, so 2x, minus the square root of the second thing, which is 5. Multiply that quantity by the square root of the first thing, plus the square root of the second thing. Now here's the thing about factoring. It's usually, it's easier for, well, when you're dealing with very complicated things, it's always easier to multiply than it is to factor. When you're dealing with very basic expressions, you might not notice much of a difference. But for large things, it's easier to multiply than it is to factor. So what we can do is we can always just multiply things back. Once we've factored our expression, we can always just multiply stuff and see if we get back what we started with. So let's try that. 2x times 2x is 4x squared. 2x times 5 is 10x. Negative 5 times 2x is negative 10x. And then negative 5 times 5 is negative 25. And the 10x's cancel. This is, in fact, what we started with. So we did it right. Yay. Here's our check mark. Okay, so that's how we're going to do factoring, is once we factored, we're just going to check by multiplying everything back together and seeing if it comes out right. So the next one is x cubed minus 3x squared minus 4x plus 12. And so for this one might be a little harder for us to figure out, but we have some techniques we can use. So the first technique would be to check to see, is this one of the forms that we know? Like, is it a difference of squares? We should know that. We should know what a perfect square looks like as well. This, however, has a cube in it, so it's not going to be that form. We might remember what a perfect cube looks like, or a difference of cubes. This is not a difference of cubes, by the way. Differences of cubes look like differences of squares, except that instead of it being a square minus a square, it's a cube minus a cube. So this is not that. There are a few forms that we can know. If we don't know our cube forms, then we might have to rely on a technique called the rational roots theorem. Okay, so we're going to test this out. The rational roots theorem says that if a function has if a polynomial has a rational root, then that rational root will be of the form one of the factors of the denominator divided by, one of the factors of the constant, there we go, that's a constant, divided by one of the factors of the coefficient on the highest power term. So in this case, that's going to be 1. So what are factors of 12? They're 1, 2, 3, 4, 6, and 12. What are factors of 1? Well, 1. And the other thing the rational roots theorem says is it might be positive or negative. So we just have to check this number divided by this number and check it positive or negative. This number divided by this number, and if it's positive or negative. The rational roots theorem, if these two numbers have a lot of factors, it can still be kind of tedious to go through all of the roots from the rational roots theorem. However, this one's not too bad. We have it's not going to be too long to check it. So what we want to do, let me clear off all of the scribbling. So the numbers that we want to check are plus or minus 1, 2, 3, 4, 6, and 12. Divided by 1, but that doesn't do anything to them. So it's going to be this list. So let's see. If we plug in 1, what do we get? 1 minus 3 is negative 2, minus 4 is negative 6, plus 12 is not 0, so 1 doesn't work. Let's try negative 1. So we have negative 1 minus 3 is negative 4, plus 4, because the negative 1 cancels with the negative 4 to give positive 4. So negative 4 plus 4 is 0, plus 12 is not 0. So 1 didn't make it. Let's try 2. So we get 2 cubed is 8, minus 3 times 2 squared, so that's 12. So we get, let's write this down. We have 8 minus 12 minus 8 plus 12. So the 8's cancel, and the 12's cancel, and that gives us 0. So that means 2 is a root. X equals 2 is a root, which is the same as saying x minus 2 is a factor. So let's divide this by x minus 2. So we get x minus 2 goes into x cubed minus 3x squared minus 4x plus 12. X goes into x cubed, x squared times. We get x cubed minus 2x squared. Subtract. This is just long division. X cubed minus x cubed is 0. Negative 3x squared minus negative 2x squared. That's going to be negative x squared because these negative signs cancel. Minus 4x plus 12. There we go. X goes into negative x squared how many times? Negative x times. Negative x times this is going to be negative x squared plus 2x. And we subtract that off. We get negative x squared minus negative x squared is 0. We get negative 4x minus 2x is negative 6x plus 12. X goes into negative 6x, negative 6 times. Negative 6 times x minus 2 is going to be negative 6x plus 12. And when we subtract that off, we get, well, I'll scroll down. One line just for you. Guess that's one line. Equals 0. So that means that our original expression can factor like so. We get our original expression was x cubed. Oh. We'll just clear that off. This was our original expression here. So we can factor that as follows. X minus 2 times x squared minus x minus 6. That's just this here. Okay, so now we look at this chunk here, negative x squared minus x minus 6. We say, well, what, how does this factor if it factors? Does it look like a perfect square? No. Does it look like a difference of squares? No, it doesn't. Well, we might have to resort to the rational roots theorem again. So the rational roots theorem says that the possible roots are going to be factors of the constant divided by factors of the coefficient of the leading term. So the leading term's coefficients are still 1. The factors are only 1 then. And then the constant is equal to 6. So its factors are 1, 2, 3, and 6. Now here's a neat thing. We know that 1 didn't work in the previous step, so 1 is not going to work in our current step. Let me say. So these 4 numbers divided by this number are the possible roots, but dividing by 1 doesn't change anything. So 1, 2, 3, and 6 are possible roots. But 1 can't be a root because 1 wasn't a root in the first step. So we throw that out. And that goes for -1 as well. These are plus or minus. So the first thing that we check is +2. What happens when we plug in +2? We got 2 times 2 is 4. So 4. We get -2 minus 6. What does that equal? Well, not 0. So it doesn't matter. So +2 doesn't work. Let's try -2. -2 squared is 4. -2 times -1 is +2, and then -6. So 4 plus 2 minus 6 is 0. So that means that -2 is a root, which implies that x plus 2 is a factor. So we divide this out again. However, we can probably see, looking at this, if we know one of the factors is x plus 2, we know that 2 times something has to equal 6 as our other, that's something being the constant term in our other factor. 2 times 3 is 6, so 3 is the other term, and because this is a negative, these are negative, there has to be a negative somewhere in the factorization of this. Since x plus 2 has only positives, we know that our 3 has to be negative here. So looking at this factors as x plus 2 times x minus 3. So the whole thing, we have x minus 2 times x plus 2 times x minus 3. And those are our factors. Okay. So we've been going just shy of an hour now. So I think that we will call it for today. Please do your homework. I hope that you're enjoying getting ready for calculus. If you have any questions about calculus or about getting ready for calculus, please email them to me. My email is on the screen, and I will see you next time. Bye.